All right. Well, welcome back, folks. Hopefully, you had a chance to watch the video from the afternoon yesterday. What I'd like to do then is finish up with our discussion of photoelectron spectroscopy this morning. Practice interpreting these spectrum, the spectra that we can obtain, and then make sure then that you, by the end of the period here, if given a spectrum, you should be able to interpret it fairly easily. Photoelectron spectroscopy is a good introduction to new students to spectroscopy. Spectroscopy is a very, very powerful tool, folks, that we can use, like I pointed out to you a few lectures back, that we can use to visualize something that we normally would not be able to visualize, and that is the electron. Okay? And also and so from there, then the structure of the atom itself based upon the location of electrons. So we don't actually see physically the electron, but we can deduce from the energies that we can obtain from photoelectron spectroscopy, we can deduce the location of electrons as a result of that. Spectroscopy allows us to visualize the not only the atoms but we can also visualize molecules as well. So what we do then in chemistry is that we take different information from different types of spectroscopic methods, whether it's photoelectron spectroscopy here, whether it is nuclear magnetic resonance, whether it is mass spectroscopy or IR, infrared spectroscopy. We obtain all this information to get data about the structure of a particular molecule. X-ray crystallography is a way that is a very useful method that we can use also to get three-dimensional structures as well. So we piece all of this information, we piece all of these, all of this information together to get a better idea of what the structure is of these very, very small particles. And so that's why spectroscopy, folks, and here we're only learning about one form of spectroscopy. For many of you folks who are moving on, you're going to come across these other forms of spectroscopy. And that's why I think spectroscopy, maybe if you want to think about it, next to the periodic table, is probably the second most powerful set of tools that we have in chemistry here. Okay, so there are many other ways that we can analyze, but these are very powerful tools. And so I introduced photoelectron spectroscopy here in first year freshman level chemistry, because this is easy to wrap your mind around, and you already have some familiarity with locating electrons. We did that with the atoms, and we did that here with the molecules as well. Okay, and so we left off with this discussion here, and I introduced to you this spectrum for nitrogen, and this is dinitrogen here. And so what I wanted to point out to you, and just to finish up here with the discussion, is that I wanted to show you that the information that we use to determine the the electron configuration of molecules, one was the magnetic properties, remember? And the other one I mentioned was always spectroscopy. And so each one, and so here are the molecular orbitals for nitrogen. Okay? And so these peaks here, each one of these peaks here, each one of these ranges represents these electrons here. And so the actual photoelectron spectroscopy for compounds and for elements end up being very, very complex. Not very complex, but much more complex than what we'll see. What we're going to see in class is a more simplified version. But if you notice here, then the idea then here is that the peaks here, their location represents their particular ionization energy. And remember, we can relate the kinetic energy. So remember when we talked about this a couple of lectures back, what we do is we follow the electron. We are able to obtain information about the speed, how fast the electron moves as it gets ejected from the atom. Remember, we take a photon of energy, we collide it against the atom, and that causes the electrons to get pushed out from the atom. And then the electrons follow a pathway through an electrical field, and the speed of that electron will depend upon how closely or how strongly it was held into the atom, what we refer to as the binding energy, which we learned as the ionization energy earlier. Okay, so the greater the ionization energy, the slower the atom's going to move. Okay, so you can imagine then that these atoms, the slower the electrons will move. So you can imagine then these electrons here are going to be bound very tightly, ionization energy. And so when they leave, and when during the course of the collision, when they leave, they will be slower. And so these electrons here, so this peak here represents these electrons right here. Okay, those electrons, because those represent electrons that are closest to the nucleus. It has a fairly large energy here, okay? So it represents in a whole lot of energy to remove these electrons here, okay? And so this peak here represents those electrons, okay? These 4 peaks here then, next in energy, represents these 4 right here, okay? And then finally, these 2 here are represented by this peak here. And so so that's how we were able to deduce then that the pi 2p molecular orbitals fall above the, below the sigma 2p. Remember, when I first introduced the molecular orbitals to you, the sigma 2p was supposed to be lower in energy than the pi 2p, but the photoelectron spectroscopy data here shows us that there are actually four electrons here, this grouping here, that is actually lower in energy than, and I'm sorry, let me go ahead and switch that around. So I'm used to having photoelectron spectrographs where the energy to the left is greater. So let me go ahead, let me redo this here real quickly. So here, that's this peak right here, and that's this peak right there, okay? All right, so with that said then, we have then 4 electrons here that are higher in energy than these 2 electrons here. Okay, so that's what we have. And so, lower in energy than what we have here. Okay, so what we have, okay, so these are going to be more difficult to pull out. Okay, so they represent then a greater ionization energy. These will be less difficult to pull out, and then these will be the least difficult to pull out, representing the lowest ionization energy. Okay, so we have these 2 electrons here that are low in energy, so they are going to be higher up here on the scale. Okay, so on the scale, so that's how we know that these 2 electrons that we have this flipping of these molecular orbitals here. And so with photoelectron spectroscopy, we're able to discern then, we were able to deduce then the molecular or the electron configuration for this molecule, okay, and as opposed to what we thought it would have been earlier, okay. So we used photoelectron spectroscopy, we used magnetic, the magnetic nature of this molecule here to determine then this electron configuration, okay. And that's the whole idea behind photoelectron spectroscopy, folks, is that we are able to obtain information about electron position and their energetic position based upon just these peaks here. Okay? And so make sure you keep in mind then, and we left off with this yesterday, that the size of the peak as well as the location of the peaks. The location of the peak indicates then the energies of the electrons, okay? And so the number of, however many number of peaks we have on the spectrum will indicate the number of unique electrons that we have, unique in terms of their energy, okay? And so we'll go over that in just a moment. We'll see then that comes up. But then the intensity, and the last thing I want to point out to you here then is we talked about that the intensity, which represents the height of the peak, represents how many electrons we have at that particular energy level. So this is from our POGIL activity, and we want to be able to use this information in order to interpret the spectra that we'll see in just a moment. But you want to make sure that you keep these things in mind as we move forward. Okay. All right. So what we want to do then is we want to analyze spectra, not of molecules. We could, but what we're going to do is we're going to start out fairly simple. We're going to analyze spectra of very simple atoms. Okay, so we're going to do atoms first, and we're going to see then that the spectra that we're given will allow us to interpret the location, that is the electron configuration of each one of these atoms themselves. Okay, so let's go ahead and let's start out with carbon here. Okay, so we have carbon. This is a single carbon atom. The electron configuration for carbon, remember, and we said that was 1s2, 2s2, 2p2. So 6 total electrons for carbon here. Okay, so 6 total electrons. And when we do photoelectron spectroscopy, we want to locate all of these electrons here. Okay. All right, so I have overlaid for you here over the carbon atom. Okay, and so this represents then the 1s. So if you take a look at this, this is the 1s orbital here. This is the 2s orbital here. And this is the 2p orbital here. Now remember, the 2s and 2p, and we'll go over this in just a moment, they are different in energy, 2p being a little bit higher in energy than the others. Okay? All right. So then with that said, if you notice here, and let's go ahead and highlight this here, folks, we have, first of all, okay, these electrons here, these two electrons here, and let me go ahead and write this in here for you, that are closer to the nucleus, which means then you can imagine, since this is closer, the R here, the radius here is closer, these will be held more tightly. These will have a higher ionization energy than these two out here. And as we move out, they're moving further and further out, we can imagine then the ionization energy holding these two electrons here will be less. And finally, the ionization energy way out here, okay, for these two electrons will be even less. Okay, so so that means that as we move out from the nucleus, as the distance gets further and further away, okay, we saw then with Coulomb's law, then the energy that binds it is going to be lower and lower. So therefore, then the ionization energy for the 1s, is going to be greater than the ionization energy for the second, which is going to be greater than the ionization energy for the third. Okay, and so remember we said then the location of the peaks then represents then the ionization energy. So if you notice here, then this is the energy here, this is energy here. Energy increases as you go from right to left, and that's why I pointed out to you on the previous slide. This is what I'm used to. The previous slide then had the energy increasing from left to right. Okay? All right, so this represents the highest energy electrons, this middle and this third. So based on that alone, you can recognize then that since this is as highest energy, this peak here represents the 1s electron. Okay, therefore this peak here represents the 2s, and then finally this peak here represents the 3s. This is going to be furthest upfield. Okay, so this is going to be furthest upfield, meaning it has the greatest energy. So this is going to be upfield here on this side, downfield here. Okay? And so this then represents then the lowest energy electrons, and that's the 2p here. Okay, and so that's how we can locate. We can locate these peaks here, and we can locate their electrons based upon their position on the photoelectron spectrum here. Okay, so so this is what we have here. Okay, and so I like this diagram because it allows you to see then that this peak here corresponds to these electrons here. This peak here corresponds to the 2s orbital here, and these represent the 2p. Okay, all right. So there we have it. We've located the peaks, and we've located the which electrons they refer to. Okay. Now the size of the peak. If you notice here, then the intensity of the peak here, all of them have the same intensity. So if you take a look at this here, they all have the same size. They all have the same height. Okay, and so that means then they all represent the same number of electrons. Okay, and so you can see here then that and this is kind of an arbitrary thing that we've said then, that since we know the electron configuration for carbon here, okay, we're going to translate this back, and we're going to say then that each one of these each energy orbital, we have the same number of electrons. Each peak should be the same height as well. Okay, so there it is. So when we look at a spectrum, we want to find the location of the peaks and make sure we can interpret them in terms of their energies, and then also the sizes of the the sizes of the peaks as well, and use that to determine then their the number of electrons that they refer to. Okay, all right, let's go ahead then, and what I would like to do, let's keep practicing this, folks, here. So we did this for carbon. So with that said, then I just want to point out to you then, make sure you to highlight a point here again for you. Okay, 1s is, remember, 1s is lower in orbital. The 2s and the 2p are all separate. Okay, so the 2p are higher in energy than the 2s, and the 1s is lowest, has the lowest on the energy scalar, which means that it's closest to the nucleus. Meaning that if it's closest to the nucleus, it's going to have a larger binding energy. That's what you want to make sure you understand. When we say this, then this is going to be the most stable. Okay, that means then as we go down here, the nucleus, remember, is down here. This is going to be closest to the nucleus, and that's what we have right there. Okay, so the 2s and the 2p are separate from one another, and so the 2p is a little bit further away from energy, further away from the nucleus than the 2s orbital. Okay, all right, very good. So let's go ahead then, and let's take a look at another. Okay, so the photoelectron spectrum can be used, and to make sure you understand, we can use this to interpret the atom. we can use this. So let's say you don't know what the electron configuration is. You can use it to interpret it based on what you know. Okay, all right. So we can use it. We got to make sure again we locate the peaks, know, and then make sure we can interpret the relative size of the peaks as well. Okay, let's take a look at this here. Okay. So let's go ahead and take a look at this particular the spectrum for this particular atom. We don't know what the atom is. In the previous one, I told you it was carbon, and we were able to use that information to relate peak to the electron. Okay. What we want to do here then is we want to be able to, if you're given this spectrum here, could you deduce what the atom is? Okay. Well, let's first of all make sure you understand that we have 1, 2, 3, 4, 5. So we have relative number of electrons and binding energy here. Okay. But what we have then is we have 1, 2, 3, 4, 5 unique peaks. Okay, with this one here being the highest energy. Okay, and remember, highest energy meaning closest to the nucleus. Okay, so we have then a highest energy, and what I've done here is I've labeled for you the possibilities here. So usually the one highest at energy is that requires the most energy here is going to be closest. That'll be your 1s orbital. Okay, so you have electrons here in the 1s. You have them moving out, then 2s, 2p, 3s, and 3p. Okay, so we have that right there. So 5 unique peaks. Right, so with that said, then if you notice here, the size of the peaks is going to help us here. Okay, seeing then that the 1s, 2s, 3s, and 3p are all the same size, and roughly the 2p here is about maybe 2 times larger than each one of these here, about twice as large. Okay, so you can imagine then that this would mean then that if and we know then that if we're going to fill in all these orbitals out here, that the 1s here then it's going to represent 2 electrons. Okay? The 2 electrons here. Okay, so that means then all of these peaks will represent then 2 electrons. Okay, yeah, I'm sorry. I'm sorry. 3p is a little bit higher. Let me go ahead and erase that one. Sorry, a little bit higher. Okay, but all of these here, the 1s, the 2s, and the 3s all represent 2 electrons. Okay, all right. So with that said, then we said that the 2p here is about twice as large as this. Okay, so we can say then that this represents then 4 electrons. Okay, I'm sorry, 3 times bigger. Sorry, and this is going to represent then 6 electrons here if it's 3 times larger. Okay, so we have 6 electrons here, 2 here, 2 here, and 2 here. And then finally with the 3p, then this looks like it's just about a little bit bigger, but a little bit bigger than this one. So not twice as large, so we can say that there's 3 electrons there. Okay. All right, so with that said, then what we have here, let's go ahead and write down what we have based on that, what we've written here. In the 1s orbital, we have 2 electrons, okay, based on the size. In the 2s orbital, we have 2 electrons. Okay. In the 2p orbitals, we have 3 times as many. The peak here is about 3 times larger than this one, so it'll be 6. Okay. We have a 3s 2, and then the 3p 3. Okay, so with that said, real quick on your paper, folks, with that electron configuration, what atom has that electron configuration? Take about 15 seconds, write down what you think that is. So go ahead and find that. I think it should be pretty easy for you to find. Write down on your paper what atom has that electron configuration. Okay, hopefully everyone see then. You just add up these add up the exponents here. You have 6, 10, or 15. Okay, so 15 electrons then represents magnesium. So this is the electron, this is the spectrum for magnesium. Okay, all right, so let's go ahead then and let's see how that corresponds to the magnesium atom. Let's go ahead and I'll pull down the magnesium atom here. So there's your, I'm sorry, phosphorus. Oh boy, it's gonna be sorry folks, it's gonna be a rough morning. Okay. So phosphorus, okay, that's why I need you guys here. We need to be back in school so you guys can help me out. That's what you normally do when I make these simple old man mistakes. You correct me for it. So this atom here is going to be phosphorus. Okay, so we have then let's see, 10, 15. 15 is phosphorus, not magnesium. I apologize. Okay, so this is the electrons. This is the spectrum. This is the photoelectron spectrum for phosphorus. Okay, so here is our phosphorus atom. Let's go ahead and link each one, relate each one of these to the atoms themselves. Okay, so let's take a look at the first one. Okay, let me go ahead and do this. Let's take a look at the person. So the first electron here, first two electrons here corresponds to those two electrons here closest to the nucleus, like we pointed out. Thus, it has the largest, the greatest binding energy, the greatest ionization energy. It's going to be furthest upfield, okay, furthest upfield in terms of the energy. And there's what we have. Okay, all right. The 2s, so the next one up would be then the 2s orbitals, 2s electrons. And so there are the 8 out here. We'll just arbitrarily call these two here 2s, but they're going to be, they're going to have a slightly less energy than the 1s because they're a little bit further away from the nucleus, okay? But they will have more than the remaining 6 here. So the 6 2p electrons here will represent those remaining in the 2s orbital, the second energy orbital there. And so they will have a slightly lower energy. They're a little bit further away from the nucleus. And so they have a slightly less energy, slightly smaller binding energy than the 2s orbitals here. Okay? Right, moving forward then, the 3s electrons will be those out there. Okay, so they're a little bit further away from the nucleus. The binding energy will be a little bit less. And then finally then we have these 3 electrons here. Okay, which represents the 3p, those 3 electrons there. They are, remember, the 3p are a little bit further away from the 3s, so therefore their energy is going to be a little bit less. Their binding energy is going to be a little bit smaller than the 3s electrons here. Okay, and so that's how we go about, folks. Then using the photo. So if given an atom, we should be able to relate that to this spectrum. But if we're given a spectrum, we should be able to interpret it and get the atom, okay, and be able to do that. And that's what we did here. So what I would like us to do here then, let's practice this really quickly. Okay? Let me go ahead then, and let me ask you to do this. Okay? I give you the spectrum for magnesium here, okay, and then I give you the atom here for magnesium as well. Okay, so what I would like you to do then is real quickly, with the 4 peaks here, relate them to the, and just draw them, just go ahead and refer to them here. Which peak refers to which atoms here. So take about a couple minutes to get this, about a minute to get this done. We're running a little low on time. I'll continue with this in the afternoon. So please make sure you join us in the afternoon. Watch the video in the afternoon, and we'll practice some more. But go ahead with the remaining time that we have here. I want you to relate these 4 peaks to the atoms, to the electrons in the magnesium atom itself. Okay, so go ahead and get that done, and then we'll go over it. Okay. All right, so let's go ahead and take a look at this here. We have, let's write this down here. We have 1, 2, 3, 4. This peak here is furthest downfield, furthest upfield here. That means it has the greatest binding energy. This one represents the highest binding energy. Okay, which means then, folks, remember, if it has the highest binding energy, it's going to be closest to the nucleus. So this must represent then the 2 electrons here, the 1s electrons. Okay, all right, moving out then, we have then this peak here. So this has the energy of 1.26, 126 megajoules. So this is the 126 megajoules per mole. Both of these electrons here represents that peak. Okay, all right. Moving out then, we see then we have another peak right here, same size as this peak here, which means then if this represents 2 electrons, this also represents 2 electrons, okay? But it's a little bit further away, as the binding energy is a little bit less, and so it's going to be a little bit further away. So therefore, we can imagine that in the second energy level here, let me just change colors really quickly so we can differentiate. I'm sorry, let me go ahead and do a different one. Okay? This represents and must represent then the 2s. So this is the 2s orbitals, same size, and then there has to be 2 of them, okay? And so let's go ahead then and let's just pick arbitrarily 2 there. That represents then the 9.07 megajoules per mole peak, okay? So those here. All right, so then if you take a look at the next peak here, we have then a peak that is 1, 2, 3, roughly 3 times larger than these, okay? 3 times larger than those. And so let's go ahead and label this one. So this one must be then and it's a little bit further away, so this must represent then the 2p, and there should be 6 of those, and so therefore we have 1, 2, 3, 4, 5, 6. So these represent then the peaks at the peak at 5.31 megajoules per mole, and that's all of these electrons here, the remaining electrons in the second energy level there. So those are your 2p electrons right there, and there's 6 of them, and the size again of this peak and its location indicates then that it is the 2p electrons. Okay? All right, then finally, then we go back. And let me go ahead and let's point this out here. We have this peak here. It is furthest downfield, okay, furthest downfield, which means then this is going to, this means then these are the electrons that are furthest away from the nucleus. And so this must represent then the 3s electrons. And again, it's the same size as this peak here and this peak here. So that must represent 2 electrons. So therefore, we have those 2 electrons there, which has a energy of 0.74 megajoules per mole. Okay, and there it is. Now we've located each one of these electrons, and we've identified each one of these peaks and the unique electrons that they represent. So interpreting photoelectron spectroscopy, I think, is fairly simple as long as you can determine then the relative sizes and the location of these peaks and correspond those to the atom and to the electrons on the atom itself. We'll practice this more after school in the afternoon session today, folks. Okay, so we'll practice more in the afternoon session. Please watch that. You're going to find then with the homework that I've assigned for you tonight, it'll give you a chance to practice. But you're going to find then that photoelectron spectroscopy can be fun. It's a great way to interpret it, and you get your first experience with spectroscopy. And unfortunately, we don't get to run these experiments, but it's really cool to be able to connect peaks, these random peaks on a graph to the actual structure and electron configuration of the atom itself. So we've learned about electron configuration. Now we know how. Now we're learning about the experimental data that supports our electron configurations. Okay. All right. Very good, folks. So I will see you after school in the afternoon session today, and we'll continue with the interpretation of these spectrum. Okay. All right. Have a good morning, folks. I'll see you this afternoon.